Okay, well, welcome back. I hope everybody is sufficiently caffeinated, or will be in about an hour or so. So what I'll be talking about today is I'll dive a little bit more into modeling. Mike talked a lot this morning about forecasting, and he definitely talked about modeling, but I want to drill down a little bit more into it. And I will say that I deliberately did not pick examples that were too mathy or ecologically, because I find, especially when you work in a field for long enough, it's important to take a step back out of the details and try to make sure that you're maintaining a good mental model of what you're doing, so that, when you talk to non-specialists, especially if you're dealing with policymakers, you have a really good, succinct way of explaining to them what you do. So with that in mind, if you are, hungry for technical details, I'm sure Mike and Mike will give you them later today. This is going to be a much higher level overview. So the questions that I want to guide our lecture today, or this talk, are the following. So first of all, what is a model? What makes a model good? And we will get into this a little bit later in the week when we talk about model evaluation, but I'll just talk more on a high level, as I mentioned. What is the process of modeling? Mike definitely gave us a taste for that a little bit earlier today, but I'll talk about that a bit more as well. And then what types of models are there? There are lots of types of models, lots of different ways of classifying models, lots of pros and cons. We'll talk about a few flavors that might come up this week as we work. Okay, what is a model? Very deep foundational question. Actually, you know what? I feel like I'll have time. Why don't we open the floor? Let's make this a bit more interactive. So does anyone want to take a brave stab at what a model is in general? I know it's hard to be the first one to talk. So I'd rather not be the only one talking for this hour. Yeah.
Some kind of representation of an organism or system.
Cool, a representation of an organism or system. I really like that word. That's going to come up. Anyone else? Maybe that was the perfect answer. Maybe there is no better answer. Thank you. So I'll say that these are all models. So we have, well, I know this is actually very topical because of the Barbie movie, but I made this slide like 2 years ago, so I was ahead of the curve, I'll say that. So we have a map of Hamilton, which is where McMaster University is, where I did a lot of my schooling and am now adjunct. There's a model up here. Who knows what that model is? I'm guessing some people here do. The one up here. Is that familiar? For exponential growth, very good. I know it's hard when you slap a bunch of symbols and you don't define them and someone asks you what is this, but we often use the same symbols in textbooks. So what about this guy here? What's this probably? Linear regression, very good. And then that, what's that a model of? The perfect woman. It could be, I mean, some people might look at it as the perfect woman, and some people might see it as a symbol of feminism. There's like lots of different ways to slice it and dice it. That's true of all models, right? They can represent, depending on your perspective, they can represent different things. I mean, linear regression is widely used to model many different phenomena, right? Because we've abstracted away from the detail. So that's what these things have in common. As one of our wonderful audience members here said, all models are representations of reality, right? They're not reality, they're representations, and that will have its own pros and cons. Okay, so we already kind of went through this, so I will skip this over, but or maybe I'll go a little bit deeper. So what are some examples where we use like an exponential growth model in ecology, let's say? For population growth, reproduction, bacteria reproducing, for instance. And I know the thing with the exponential model is it gets a bad rap because it seems ridiculous, right? It's like, yeah, it just predicts exponential growth forever. That's silly. But as Mike told us earlier today, the time horizon that you're predicting over is very important, right? If you're projecting out 100 years, yeah, it's a ridiculous model. But if you're doing a short-term projection of an epidemic in an early growth phase where it is exponential, it's actually a great model, and it's fast, and we know a lot about it, and we know how to simulate it, and so it can be really helpful. So I want you to always look at these models that we're talking about, and in general, as having their own pros and cons. Nothing, I mean, there's a time and a place for every model, I think. Yeah, okay. So let's keep going. What makes a model good? Any ideas before I color your judgment? So when it's simple, but it still represents a facet of reality that you're interested in, for instance. Yeah, that's a really good metric too. Simplicity can be very important because it's tractable, i.e. we can understand what causes and effects are coming from the model. Yeah. When you're explicit about why it's bad, do you have an example or a more concrete sort of? Okay. Knowing its limitations, that's a really good point about modeling. It's important to know how far you can push your model. Like when we look at the example of the exponential growth model, the time horizon is a big limitation, right? Like how far are you going to push it and how far are you going to trust those predictions? Anything else that would make a model good? Yeah. When it's useful. Yeah, that's great. That's a great example. We'll definitely talk about that. Okay, so let's move on a bit. So, okay, let's look at these maps of Hamilton. So I've added a little symbol to tell you what the main kind of focus of the map. So this is probably a map for cars. This is probably a map for buses. And this is probably a map for bikes. So which one of these is the best? It depends. What does it depend on? Your goals, how you move, what you have access to, the resources that you have access to. Not everyone has a car. Some people only have bikes or vice versa. So they can all be useful in their own right. And I mean, I like to think of maps as models because it doesn't involve equations, but they are models, right? They're representing the reality around us in a very specific way. We've encoded assumptions in these, as we do with all models, and those assumptions bear out in the results that we see. So as someone pointed out, the model quality depends on model purpose. So I'm sure we have to show this. In any sort of modeling or forecasting or anything, someone has to show this. So I'll be the person to do it. Are people familiar with this quote? Would it surprise you to know that this isn't the only, like, this comes from a textbook, and actually George Bach said this 2 different ways in the same textbook. This is the one that we usually see because it's snappy and fun, and I had a data science prof who put it on his wall in his office, and it was pretty cool. I liked it, but I found out later that actually that's not the only way he said this, and I think the other way he said it is better for our purposes. Not necessarily the best, but for our purpose. So he said also, remember that all models are wrong. The practical question is, how wrong do they have to be to not be useful? So why I like this is because it's really talking about error. How much error can you tolerate? It's important to remember that none of the models that you see are perfect or represent reality exactly. But how much error can I tolerate? If I am, an epidemic's taking off, I know it's really hard to imagine, but just imagine there's a scary new disease spreading among the population. The question is, do I have time to build, to talk to the people who are doing lit reviews and figure out what are the mechanisms, people on the ground, what does testing look like, all this stuff, and build this beautiful, complicated model? Or do I just need to do an exponential growth projection for now, and then we can kind of add on to it, right? There's, I feel like there's a quote that's like, don't let perfect be the enemy of good. That really applies to models. Is like, if you just keep waiting and waiting to build the perfect thing, you're never going to do anything. So you have to be okay with being wrong. And you just have to know how wrong you are. That's also very important. The other thing that's really important is which resources do you have at your disposal, right? Are you able to go out and, first of all, do you have the data that you need to parameterize this beautiful, perfect model that you built? Are you sure that that data is good? Do you have the computing power to simulate it? Do you have the expertise, right? There's all sorts of factors that go into it. And it's really modeling, especially when you're dealing with modeling for decision-making, often you are resource constrained, right? I mean, everyone is resource constrained. We all have limited time, right, in life. So even just that, even if you have a ton of money, you have limited time. So especially if you're trying to do something that is still relevant and topical. So that's also important to keep in mind, especially in the context of this course where we're going to have a week to work on case studies and we're just going to have to do something, right? So keep that in mind too. Okay, let's talk about an example of modeling that's going to be very different from what we're actually going to do this week. I'm sure everyone's seen some models already, but like I said, let's try to take a step back. So how long, I want to know, this is my problem. This is my decision maker request to figure out how long would it take me to walk from my old office at McMaster to a lecture hall that I was teaching in. So, I mean, I had the benefit of going to McMaster for my undergrad and my master's, so I actually knew the answer to this question pretty quickly because I had the experience. But suppose I was sort of a new lecturer, hadn't been to campus before, I might do a sort of first pass, a low resolution first pass, just get something down and then I can iterate and refine on it. So maybe all I have at my disposal, the only resource I have is this map, which unfortunately is very tiny here. But this red circle is where my office was, and then this blue circle is where the lecture hall was. So I'm looking at this map and I'm like, I don't know how long this would take me. But what I do know is actually it takes me 10 minutes to walk from this red circle to about maybe like here. So if I eyeball that, if I take that distance, which now I'm like standing on my tippy toes, but if I take that distance and kind of turn it around and try to figure out like what proportion of that 10-minute distance is that path, I might have an okay guess. So if I just look at it, I think, well, you know, that first distance is 10 minutes. The second distance is about half that. I'm going to say 5 minutes. Okay. And that might be good enough, but I'm lecturing, so I really don't want to be late, right? So I have a first guess. What I might do is a second pass, which is maybe now I've invested some time and resources to get a bit more information out of the system. So I go to Google Maps, and I know Google does give you a time estimate, but let's say they didn't. Let's say I paid someone to go and measure the path for me. I mean, I probably could have just walked it in time myself, but you know, I'm being silly. Okay, so now I know that the path is 350 meters long, and I know that, you know, adults on average walk about 5 kilometers per hour, and maybe it's a little bit more than that, but I feel like I'm a speed walker, especially when I'm like nervously going to lecture, like, oh, what am I going to talk about today, right? But let's just say that that's about an estimate there. I convert the units to make sure everything works, and I know from physics that time is distance over speed. There's my model. There's a little math for you. So my estimated time is actually 4.2 minutes, or 4 minutes and 12 seconds. Okay, well, what does Google say? They say 4 minutes, which is pretty cool. I figured out what Google's doing. I actually must have used an average for people because I definitely walk faster than that, but that's fine. 4 minutes is a little bit, maybe a bit better than a 5-minute estimate, or at the very least, it gives me confidence that my initial sort of first pass was not too bad. Now, what are some uncertainties of this guess? Let's go back one and let's look at this. What are some uncertainties in this modeling that I just did? Because again, it's always important to be aware of what are the errors. Is this the right model? I don't know. Is that physically, have we proven that with enough evidence over time to believe it? Probably, I guess. What else could be an uncertainty here? If I need to take the elevator, that's a good point. I don't know about anything about what's going on inside the buildings. I haven't thought about that. So that's not in my model. Yeah. Sorry, you in purple shirt. There might be construction. That is, yeah, that is a fair guess. On the campus, there might be construction. Very good point. Yeah, this route might be obstructed in a way that I can't maintain an average of 5 kilometers per hour pace. Yeah. I might bump into red lights. Yes, if there are any stop or crosswalks or anything I have to cross, that'll definitely slow me down potentially. I feel like someone was going to say something. No. So this also is not really the route that I would take. this is just the route that I can get off of Google Maps. But I would actually probably walk like this because I know that there is actually a path that kind of cuts across. So that's another thing. That's probably going to speed up my my trip. And what I want to point out too is, as we're talking about uncertainties, right? It's natural to think about, how does that affect my estimate? And that's another big thing. It's not just knowing that something is messing up your estimate. It's knowing in what direction does it mess it up? Does it make it an overestimate, an underestimate? And then as you kind of tally up all those uncertainties, or you put numbers to them with, you know, statistical models, you can kind of understand the net uncertainty. Okay, so now, so we've kind of run through this sort of specific example. Let's kind of be a little bit more, let's dig a bit more into the modeling process. Oh, or we can just do this instead. So my calculation gave me enormous precision, right? I was able to say 4 minutes and 12 seconds. But we have to be careful not to confuse that for accuracy, right? The accuracy of this output depends on how confident we are in the inputs. If we were really confident about that 5 kilometers per hour, like 5.00 kilometers per hour, maybe we could trust this estimate. But this is probably, you know, we're maybe a little bit overconfident with how precise we're getting. And that's really important when you're talking to decision makers, because often people who have not spent a lot of time thinking about math and stats will see numbers. People in general, like even us, like I would say, like people who have spent a lot of time with numbers, will see numbers and think, oh, it's a number, it's measured, it's scientific. There's like a bit of like a science washing effect that can go on, where you can present something in a very technical way and it makes people believe that it is, in quotes, true, right? So it's very important to be careful how you frame and contextualize your results for anyone, especially people who are making decisions. And yes, we kind of talked about this a bit. We might not know the size of the errors, but we can at least think about what direction are those errors pushing the estimate. That can also be very helpful. Okay, so what is the process of modeling? So we got a little teaser earlier. I like to think about this. Modeling is kind of the process of mapping between the real world and a mathematical or statistical framework. So here's a little very official diagram. The way that I think about it is we have the real world, which is very complicated and messy, as I've clearly denoted with these loosey-goosey circly things. And then we have model world, which is beautiful and idealized and crisp. And where modeling happens in a cycle, but what the hardest part, in my opinion, of modeling is the translation step, where we're taking something that's messy and real and converting it to something beautiful and idealized. That's where a lot of this sort of art of modeling is happening, because you not only have to simplify and make assumptions, but you have to simplify and make the right assumptions for the question you're asking. And that involves a number of skills, including domain-specific knowledge. Like, you have to know something about how diseases spread in order to model them, right? I mean, maybe you don't, I don't know, but I feel like to model them well, you should know something about the system. And that's where that translation step is happening. So we start off with sort of the properties of the system in the real world, we translate them, then we have mathematical and statistical properties, which have their own can of worms. That can get formulated into a model, whether it's a dynamical model with equations or a statistical model with distributions. You simulate it, you analyze it, maybe you fit the model in some way, as we'll see this week, and you get some results. And now the question is, well, what does this mean? Right? Sometimes the results are not necessarily phrased like, for instance, you might get out of your model a time series of the incidence of a disease, like how many new cases do you get a day? But what does that mean for the question, the original question, which might have been, how many vaccines do we need to give out and how quickly? Right? So you still have to do some sort of translation to understand the implications of your model results on the real world. And then you have to ask yourself, is that enough? Are the results trustworthy enough for the request? Does it kind of give a good enough handle, enough knowledge, or do we need to go back? And that's where we might revisit our simplifications and assumptions and reframe the model a little bit, or we might change kind of the choices that we're making about, which distributions are we using to model this kind of noise or whatever. So a lot of the work that we're going to be doing this week is probably going to be in this first step where we're translating. I mean, that's kind of, I feel like the people who set up the case studies have done a lot of that for you already, but you're going to have to maybe revisit some of those assumptions because I think the initial models are going to be pretty simple. And you're going to have to talk about what are the implications going back to the real world of whatever you've chosen to do. Okay, so just to say, like, it's going to be an iterative process, and just keep that in mind, and don't wait to get the sort of put all the bells and whistles in and then look at the results and then you don't know what's going on, right? I'm going to stop here and ask if there are any questions. Okay. So let's go to a bit of a more complicated example. So does anyone know what this is a diagram of? Just off the top with the annotations and stuff a predator-prey model, yeah, a Lotka-Volterra model. Very good, yeah. So we have rabbits, which are the prey, and we have foxes, which are the predators, right? So the rabbits in this idealized math world, the rabbits are born according to some birth process. Often we just assume an exponential process because it's probably fine for the purpose. And they die off. And we're going to assume that actually all of their deaths are attributable to predation by foxes. We're not going to assume that they're eaten by anything else, or perhaps that they die, after a nice long bunny life, they die of natural causes. That's kind of not what we're picturing here. So all of the deaths are actually coming from interaction with foxes. And then the foxes, obviously, as they eat the bunnies, they're going to reproduce from that, energy that they gain. They're going to live longer lives, and they're probably going to produce more offspring. So we're going to assume that all of the births for the foxes are coming from, based, down the line from interactions with rabbits. So the more that they eat the rabbits, the more that they're going to reproduce, and vice versa. If they don't eat that much, they might not reproduce as much. And then their deaths, we're going to give them a nice, peaceful, long life and let them die of natural causes. So this is the model in terms of the picture, but we may choose to cast it in terms of equations so that we can actually simulate it. So often this model is seen in the context of ordinary differential equations. There are other ways to cast it as well. You could do difference equations. You could do, I don't know, something else that I haven't even thought of. You could maybe do an agent-based model, like an individual-based model. But this is sort of the idea. And the thing I want to point out is that this picture does not necessarily only map to one kind of model, even though I'm going to show one model right now. Right? This is more of a concept and idea. It's not the model itself. The model that we usually see associated with this is an ODE model, like I said, ordinary differential equations, where we look at the rate of change of rabbits or foxes over time as a derivative, and then we put rules, right? So like I said, this is the rate A is associated with the birth process. We're modeling it as an exponential process, and then the predation happens in this mass action way. If you've ever seen, I feel at this point, a lot of people have seen epidemic models, and the basic SIR model that we'll see in some case studies, it has this mass action term, which just means that we think that the rate of change for this term is proportional to the product of these two variables. And that seems to give us pretty okay results, even though it's pretty simple. And I know actually when I first saw models in undergrad, the thing I kept getting stuck on is, how do we know that's the right rule? And the answer is, well, we used it a lot and it seemed to work okay, right? So, and because I was really stuck on this concept of like models being close to reality. And I think that you kind of have to give that up a little bit sometimes and just see what works and what doesn't. And then of course, for the foxes, we have a very similar situation where their birth process is in this mass action way and their death process is just exponential. Okay. Okay, so what types of models are there? Okay. So going back to my little simple examples of models, you can look at these in different ways as different kinds of models. But if I, for instance, want to think about separating these into two different groups, what would you do? There are a lot of different possible answers here. How might you separate these? If I told you there's a secret grouping, it's not necessarily 2 and 2, it could be, and you can put different labels on them, what would you do? The math ones and the not math ones, yeah. The ones that are easily represented by an equation and the ones that are kind of pictorial, absolutely, that's one. There's at least another one. Graphical or non-graphical, sure, yeah. But okay, let's dig into that more. Instead of graphical, what if I said one grouping was descriptive models? Which ones are descriptive here? And what's the opposite of that? Or at least not necessarily the opposite, but another facet. I would say they could all be predictive in some way, but that's not a bad guess. Analytical. Oh, that's an interesting word. Yeah. Now we're playing like word association. No, I mean, I kind of see where you're getting at. I think we're circling around it. I'll give you guys the answer. So I would say that these lower ones are descriptive or phenomenological. You might have heard that word before. And the top one is mechanistic or rule-based, right? Like I said, there's lots of different ways to think about these models. And that's some of what makes modeling hard, right? Is it can be very abstract. So let's talk a little bit more about each of these types of models. So phenomenological models are, one very famous example is linear regression, right? It's a relationship that describes a correlation, not necessarily a causation, right? These describe the state of a system at one or various points in time, but the key word here is descriptive, right? We're describing, we're not necessarily understanding why the system is that way. We're also trying to capture what the system looks like and not why it looks that way. I'm telling the future in my own lecture here. We don't necessarily need any domain-specific knowledge or context to formulate these models, and that's really powerful. I know it can be tempting to say, oh, these aren't as good as that model or whatever, but that's not really a helpful thing, right? The question is, when is this useful, right? So we don't necessarily need to know, too much about the variables X and Y if it looks like there's a linear relationship, right? We can just perform a regression and get some inference out of that. Now, we can use phenomenological models for prediction via, let's say, extrapolation, and we should sometimes, absolutely. But without any idea or context of how the data is generated, we could be very wrong about that observed relationship, which is why it's important to keep forecasting, right? And keep trying to get better and better at what you're doing. Now, mechanistic models like this exponential model, here we try to actually come up with rules that explain the observed behavior of the system, right? So in essence, we're trying to capture how the system behaves and why it does behave that way. Here we definitely need domain-specific knowledge and context, because if we don't have that, we can't come up with rules about the system. So for instance, here's an example that Corinne gave me that's really nice, that we're thinking about the position of a grasshopper over time as it jumps, right? And maybe we only observe this first part. That first part looks awfully linear, right? So it kind of makes sense, like there's a bit of there's a correlation between position and time in that observation that's linear. So if you were to, do a linear regression and predict ahead in time, you would just get that the grasshopper is going up. And maybe for a time it will continue to go up that way, right? And it's not a terrible prediction. But at some point in time, if you've studied grasshoppers, you might realize, well, actually, their flight, or if you've studied physics, I guess is probably better, their flight is affected both by drag, this force of the air that's, they're traveling through it and it's pulling back on them, and also the force of gravity. So you could, come up with some rules and equations, and you could actually correct your correlative prediction to be this other trajectory. And you'd still probably use information that you gather from the initial prediction, but you can see that those two diverge. So if you're not careful, you can mislead yourself into thinking that things are straight forever, or whatever the trend may be in the observed data. So often people look at, you've probably seen examples of mechanistic and phenomenological models or descriptive models in classes or in your work or whatever. We have process-based mechanistic models, like this is a variant of the SIR model for infectious disease. Here we have a representation of perhaps a spatial model where we're tracking, or an individual-based model with some spatial component where we're looking at individuals, maybe how they move in a planar space over time. But there's some rules governing that movement, for example. Or we have these pattern-based models, like they can be as simple as a linear regression, or they can be as complicated as a neural network, right? Where we actually, it's almost like a black box where we don't really understand what's going on or how it's going on, but we have some output that we could look at predictions from. And the way that we classify, there's lots of different ways to look at these types of models, but I like to think about it on an axis, two axes. So interpretability and then level of domain-specific knowledge required. So for example, neural networks are not very interpretable, but you don't need a lot of knowledge to get started with them. So in an information not information sparse setting, but in a setting where we don't really understand the system very well, we could usually get pretty far with these things. On the other hand, sometimes we don't understand it well enough and then things go haywire. If you move on, you get maybe a linear regression is maybe a little bit more interpretable because there's fewer moving parts, so we can kind of understand what each of the variables that are coming out of the model are saying, or rather the parameters that are being fitted to the model. And you don't really need too much domain-specific knowledge, but I'd actually posit that you need a little bit more than with, let's say, a neural network, because you have to know what are the important covariates, right? If you're building a neural network, you can throw as many covariates as you want in there and get a result, but you need a little bit of understanding of the system to get to a point where you're like, well, maybe we don't use this variable or that variable, and that actually could improve your prediction. And then again, maybe a bit more interpretable when you have a rule-based model, even if it's complicated. But again, if you're using, let's say, an agent-based model for infectious disease spread, you might not actually need as much domain-specific knowledge as something simpler like an SIR model, because again, an SIR model, you're kind of reducing dimensionality in a way, like you're pulling out just some key mechanisms, and so you don't need everything in the kitchen sink. You need a bit of understanding to do that. So don't mistake this axis as level of information required, because certainly you need more data and information for these really complicated models, but that's not the same as domain-specific knowledge, right? Okay, so we've kind of set this up, at least from this slide, as a versus. But what I want to say here too is that it's not one or the other, and it doesn't have to be one or the other. And actually they have a bit of a symbiotic relationship, both in the modeling process and more explicitly. So if we think about the modeling process, you might gather descriptions of the system that you're working with, perhaps do some phenomenological modeling to get a better handle of maybe what are the important mechanisms and variables and effect sizes and all this stuff. And then you might propose a mechanism and say, it looks like this variable really affects the outcome. Let's think about why that is. Like, what are maybe the physics in the system, or the behavior, or whatever it is. And then you generate predictions and compare to the original descriptions and gather new ones and kind of go back into that cycle. And then you might propose another mechanism. So these two modeling approaches can actually work together in the modeling process, and on and on and on. But they can also be used explicitly together. So here's a figure that talks about predicting species occurrence it's an ecological niche model. So we're thinking about there's a species that we're studying maybe, and we want to think about in a geographical region, where are we likely to find it, right? So one approach is correlative or phenomenological, where we look at maybe climate data and where those species are already found if we've sampled some of the geographical space. And we can come up with some correlations between, for instance, temperature and precipitation, two metrics that we can measure directly. And we can look at the correlation of those with occurrence and come up with some prediction of occurrence in other unsampled geographical areas by extrapolating from that model, right? That seems pretty sound. The other approach, which is kind of on the other end, is mechanistic, where we take the climate data, but we also take the biology of the system through maybe some genotype, phenotype information, information about the organismal condition and how those are related. And then we can come up with these sort of metrics that could then be used with some kind of rule-based model to come up with fitness. What is the fitness of the organism given body temperature and water balance in that region, right? And then that fitness will give us a prediction of where we should find that organism. But the hybrid approach, which actually makes use of both of these things and maybe makes use of advantages of one and not the other. For instance, people spend a lot of time in biology studying organisms, and you want to leverage that knowledge base. So what you might do is you might come up with metrics that are informed by some rules or a mechanism, like net energy intake and thermal stress index in this example. So those metrics come about based on rules and calculations that are, related to, for instance, fitness. But then you use correlations with the occurrence, because you can't necessarily go out and measure these, rule-based metrics, but you can calculate them from other observations, and then you just find correlations, and you can do another sort of probabilistic occurrence prediction. So there's another example that these two things don't have to be at odds. They can actually work together really well. So other ways to characterize models. So we have dynamic or static models. So dynamic models are if there's a time component, which in this course we'll definitely be dealing, I think, with, actually, I don't know that. I feel like most of the case studies have some kind of time component. Awesome. But there's also static modeling. Like, a linear regression is an example of a static model. We've taken a snapshot of observations and we've modeled them. That's fine too. There are discrete or continuous models. So for instance, they might be discrete or continuous in state. So in stats, we talk about categorical or numerical variables, right? Categorical ones are discrete. Numerical ones live on a spectrum. Arguable that, there are actually discrete variables out there, but anyway. Or they could be discrete or continuous in time. So for instance, here is a difference equation where we've taken the time domain and we're looking at things in discrete steps, maybe seconds, minutes, days, whatever. Or we look in the continuous domain where we can come up with things like differential equations where we're looking at rates of change in terms of on a spectrum, on a continuum. And what I'll just quickly point out is that simulations that we put into our computer, even if you have a continuous model in hand, when you encode it into the computer, because of how computers work, they discretize numbers, even though they live on a continuum. So all the simulations that you'll be producing will be discrete in time. And we will use those as approximations for the behavior of the continuous system. That's important when you run into issues with numbers. And of course, we have deterministic or stochastic models. So often you might start with something like a deterministic model. So in epidemics, an SIR model is just usually written down in a system of ordinary differential equations, which are deterministic. So whatever my initial condition is, if I put in the same one into the same set of equations, I get the same answer out. But in some cases, in most cases in real life, we often add a stochastic component, like maybe observation noise or process noise or other measures of uncertainty that will mean that when we simulate that system, we can start with the same initial conditions, but we'll end up with a slightly different answer down the line. So the key question is there noise incorporated in the model? So just to quickly summarize, what is a model? It is a representation of reality. What makes a model good? It will depend on the purpose of the model. Oops. And later on in the week, we'll talk more about quantifying the goodness of the model that you're using. I'll also mention that there's a bit of a semantic issue here, because personally, when I say a model, I'm thinking of an SIR model, like let's say, like qualitatively, this is the model, like this is the shape it has, and this is kind of the mechanism or whatever. But sometimes people will say a model for, this is the SIR model with these specific parameters. That's our fit. That's our model for that. And we can update it by refitting or whatever. So just it's something important to keep in mind when you're talking, let's say, to your colleagues about what's the model being used. They might be being more precise than you are. Like they might, I always work with some variant of an SIR model, but my fits are always different depending on the observations. So that can be a bit of a different thing. And then what is the process of modeling? I gave you a little picture. We saw other pictures earlier today, but I think the key thing is that it's going to be iterative. We've seen that a couple of times now. And then the types of models. So this is just, I'll say this is just a very abbreviated list. There are many other ways to look at models, and I think these are probably the most relevant for the kind of work that we'll be doing this week. But yeah, that's kind of that. And I think what I'll do is, I apologize that the talk is shorter than we thought. I wasn't sure how long it would go in the end. But what I'll do is I will open the floor if anyone wants to ask me questions about this talk or Mike about the forecasting talk earlier. If, I don't know if Mike wants to come up or not, but either way, that's it. If anyone has questions, yeah.
So do you have a dynamic model without a time component?
No, I think by definition, dynamic, like mathematical definition, I think it means with time. But maybe my point of view is narrow and someone else has an example that I can't think of. I think that's usually what it, by definition, it means, yeah. Dynamic in space. Yeah. I don't know. Yeah. Yeah, I guess like state dependent sounds like a term that you would use there. I don't know. Yeah. No one has any questions about modeling or forecasting. Well, then I guess we're done. We can all go home. I'm kidding. Yeah. How the rules are decided. Sorry, who? Sorry? Yeah. Yeah. Honestly, I mean, I think it comes with experimentation. Often, I think what happens is, I mean, a lot of these rules that we use now all the time, like, you know, with exponential growth or mass action, those are rules that were proposed a very long time ago. And it just, you know, perhaps a long time ago, someone saw some data and, you know, maybe it was like, oh, this kind of looks like it goes exponentially. Well, why might it do that? Well, oh, it looks like a bacterium, you know, will separate into two. So from one you create two, and then from two you create four. And so, you know, you kind of, I think it's just, it comes from curiosity and experimentation, and it's definitely usually informed by experiments, like scientific experiments as well. I don't know, Mike, do you have anything else to add?
I would add that there's a lot of advantages to proposing multiple alternative models that represent different hypotheses about how you think your system works, and then confront them with the data.
Yeah.
So early in a forecasting process, you might have many candidate models that are equally compatible with the data, and over time, over time, some are likely to be more compatible than others. All of them might be wrong, and you might have to evaluate the models to figure out, you know, where all of the assumptions are wrong. But yeah, multi-model on forecasting is definitely has a lot of advantages, particularly when you have uncertainty about the model structure, which you always do. I think that's also one of the advantages, which I don't think we really dive into in a lot of detail in this course, of these ideas of hybrid models, of trying to combine the strengths of mechanistic models with the flexibility of machine learning models to create models that ideally have the best of both worlds. You know, they represent your knowledge, but also have the flexibility to capture systematic patterns to where your understanding is incomplete. But you know, some of us were at a conference a couple months ago on the Gordon conference, and it was interesting to see like where the hybrid models were beating every other approaches and where they actually weren't, where a hybrid model actually performed worse than the mechanistic model alone, or worse than the machine learning model alone, because they're often touted as like, you know, they should in theory always do better than either alone, but they don't always.
It's interesting you say that. If we think back to that slide you showed about progress in weather forecasting over time, I don't know if people were really looking at the numbers, but there was like the first 20 years, the forecasts were not better than flipping a coin. They were less than 50% accurate. So it takes time, right, to get to that point where, you know, it could be this new and exciting thing, but it can take time and iteration to really get to something useful. Yeah.
I have a question. It's kind of related. I know that the whole workshop is about forecasting, like the course, but I'm also interested in like how much working like methods with causality you make before like jumping into forecasting, and like, because I feel like if you just want a forecast and you can just drop everything into some kind of like machine learning model and get like predictions. But I feel like very often I also see these papers kind of criticizing like not like understanding all the causal relationships and then jumping over to forecasting. Without that, how much of that do you think is actually like coming into play with policy?
I think the problem, it doesn't become when you're trying to take a correlative model and make a prediction. The problem becomes when you go the other way and you take the prediction, you start talking about what caused the prediction. I think it's the classic thing in like intro stats where, you know, you talk about, here's this correlation. Does that actually mean like it rained, therefore it's wet, right? But does it mean if it's wet that it rained? Or, you know, intro logic or something. So I think the problem becomes when people over-interpret their descriptive models and go backwards. That's, in my opinion, at least. Yeah.
Just to add on to that, so if you're thinking about the decision making you're taking here, and you're talking about alternative strategies, then really what you're saying is like you're thinking of a counterfactual, right? And so you're embedded in causal analysis right there. Because if you're saying if we take this intervention, this will have an effect, you're actually setting up a cause and effect relationship. So for me, this has actually been something I've been venturing into, and this is where causal analysis and forecasting like really come together.
I think I might add two other points. One is just kind of my experience has been that the more out of sample a prediction is, the more often people rely on mechanistic models. So if you're making predictions for things that are very similar to things you've seen in the past, then, you know, machine learning models, you know, correlative models, you know, process-based models, they will all ultimately perform similarly. But if the conditions that you're making prediction to are very different than the conditions you trained your model on, we know that machine learning models, like that's their Achilles heel, is out of sample prediction. They can't do it. They have no basis for inference out there. In the mechanistic model, if you have some belief, some epistemological belief in the mechanisms you represent, you have greater confidence that you're extrapolating based on your understanding of the process. So I know lots of people, you know, will use both types of modeling, but I find that, you know, more out of sample, the more you tend to see mechanistic models. Then on the idea of causality, there's a great paper, I really liked this paper a couple of years ago by Curry that was some title something about like what if Newton was an ecologist, and it kind of lays out this kind of series of steps that he proposes for how he would go about approaching science, and he kind of envisions this like this kind of translation from like kind of very correlative studies to predictive studies to causal studies. So he makes the argument that you would do like the causal experiments are often things you do to prove that the predictive models are actually capturing the right mechanisms. I forget the first name. The last name is Curry.
DJ Curry.
Okay. Well, in that case, I guess we can take another little break.
Yeah, we have a break, and then we start again at 11:30.